If you have ever wondered why some people get genuinely excited about Calc 3, it is because this is the point where math stops being about a line on a page and starts describing the real world in full three-dimensional. Mountains, fluid flow, electric fields, temperature, motion in space. Calculus suddenly has depth, literally. In the next few minutes, I want to show you the 5 most interesting topics in multivariable calculus, and more importantly, why they matter outside the classroom. Calc 1 teaches you how things change along a line. Calc 2 expands that into accumulation and series. But Calc 3 is where you start working in multiple dimensions at once. That changes everything. Because in real life, most things do not vary with just one input. Weather depends on temperature, pressure, humidity, elevation. A drone's position depends on X, Y, and Z. Heat spreads through solid objects in all directions. Calc 3 is the math of that complexity. First up is partial derivatives. This is one of the simplest ideas in Calc 3, but also one of the most powerful. A partial derivative asks, if I change just one variable, what happens to the output while holding everything else fixed? That sounds basic, but it is how we study systems with many inputs. For example, if a company wants to know how profit changes with price and advertising, partial derivatives let them isolate each effect separately. In machine learning, they are essential for tuning models. In engineering, they help predict how a design responds when one parameter changes. Mechanism-wise, partial derivatives let us break a complicated surface into understandable directions. Instead of asking, how steep is this whole thing? We ask, how steep is it if I move east? What about north? Next is the gradient. This is where Calc 3 starts to feel almost magical. The gradient is a vector that points in the direction of greatest increase of a function. If you imagine standing on a hill, the gradient tells you which way is steepest uphill. That is useful for optimization, finding the best design, maximum efficiency, minimum cost, or lowest error. This is why the gradient shows up in everything from economics to artificial intelligence. Gradient descent, for example, uses the gradient to iteratively move toward a minimum. It is one of the core ideas behind training neural networks. So the gradient is not just a formula, it is a direction-finding tool for any problem where you want the best outcome. Third is double and triple integrals. These are the tools that let you accumulate things over area and volume instead of just over a line. Want to find the mass of a non-uniform object? Integrate density over its volume. Want to find the amount of heat spread across a plate? Integrate over the surface. Want the average value of a function over a region? Double integrals make that possible. The usefulness here is huge because many real objects are not uniform. A metal beam may be denser in one region than another. A lake may have varying pollution levels at different points. Triple integrals let you account for all that variation instead of pretending everything is constant. Fourth is vector fields. This is one of the coolest ideas in multivariable calculus because it lets you model things that have both magnitude and direction at every point in space. Think wind across a city, or water moving in a river, or the force field around a magnet. A vector field describes what is happening at each point, not just how much of something exists there. This is incredibly useful in physics and engineering because many natural phenomena are directional. Vector fields help predict flow, force, circulation, and motion. They are the language of fluids, electromagnetism, and even traffic patterns. And finally, line and surface integrals. These extend integration into paths and curved surfaces, which is where things get really interesting. A line integral might calculate the work done by a force moving an object along a curve. A surface integral might measure flux, how much of something passes through a surface. That is useful in real systems like airflow over a wing, liquid passing through a filter, or electric and magnetic fields interacting with surfaces. It is the math behind understanding not just what exists in a region, but how it moves through space. So why does Calc 3 matter? Because it gives you the tools to model reality more honestly. Not just one variable, not just one direction, but full systems with complexity, motion, and interaction. Partial derivatives help you isolate change. Gradients help you find the best direction. Double and triple integrals let you accumulate across space. Vector fields describe flow and force, and line and surface integrals connect all of that to motion and work. Calc 3 is where math starts feeling less like a subject and more like a framework for understanding the physical world. Why Calculus 3 matters. The 5 most interesting topics in multivariable calculus is just one small part of Calculus 3. If you are interested, our full free Calculus 3 course is linked in the description.